Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to introduce tools for finding numerical algorithms that will give us approximations to analytic solutions. So in this topic, we will review the issues of using analytic formulas with numerical values. We will look at two formulas that approximate the same value, but where one formula appears to be significantly better. We will then describe tools that we will use in this course to come up with numerical algorithms and analyze their ability to find approximations to actual solutions. Now, before we introduce this topic, let us review something from calculus. From calculus, you know that the definition of the derivative is the limit we see here. And for any finite h, this formula is simply the slope of the white line, rise over run. Claim. Here's an alternative definition of the derivative. Here we have f at x plus h minus f at x minus h all over 2h. You can see that this is the slope of the white line in this image, where once again the rise is f at x plus h minus f at x minus h over the run, which is now 2h. Now, you can probably see from the previous image that these two definitions of the derivative will be the same. So in the limit, if the derivative exists, both of these should give the same answer. But you can also prove this mathematically. So this is our new definition of the limit of the derivative. We can add f at x and subtract f at x from the numerator, so essentially add 0, a trick you've probably seen in secondary school. We can now take out a factor of 1/2 out of the limit and split the fraction into 2. Now, if the limit exists, then the limit of a sum must equal the sum of the limits, again assuming each of the sums of the limits exists. So we're assuming that a derivative does indeed exist at x. Well, now we can put the limit across each, and oh, wait a second, the first one is the one approximation of the limit as h approaches x, x plus h approaches x from the right. The second is the limit as x minus h approaches x from the left. From calculus, you should know that both of these should tend towards the derivative. Consequently, we have a half times the derivative plus a half times the derivative, which is equal to the derivative. So yes, the formula we have introduced here should also define the derivative. Let's see what happens when we approximate the derivative of sine of x at x equals 1 and see what happens in MATLAB. Now, the derivative of sine at x equals 1 is cos of 1. This is the correct answer. So this is what we'd like to approximate. Now here we see a loop. The loop variable is n. So for n equals 0:17, what this does is it has a for loop that iterates 18 times, where n takes on the value 0, 1, 2, and so on and so forth, up until 17 on successive executions of the loop body. The first statement of the loop body is h being assigned 10 to the exponent negative n. So initially h takes on the value 1, then 0.1, then 0.01, and so on and so forth. There is a semicolon at the end of the statement, so this is not printed to the console. However, in the next line we have sine of 1 plus h minus sine of 1 minus h all over 2 times h. This is printed to the console. So with the first execution, well, it's not a great approximation, but it's actually sort of correct to one significant figure. With h is equal to 0.1, we're getting more significant digits of accuracy, and so on and so forth. With every single step, we seem to be getting 2 more digits of accuracy until this point. If h is made even smaller by a factor of 10 with each step, we see that the accuracy begins to plummet until our approximation of the derivative is 0. Now, 0 is only a good approximation of 0. For any other number, 0 has a relative error of 100%. But let's see what's going on here. Now, the issue here is that this does tell us that something is happening, but it doesn't tell us what is causing this loss in accuracy. What we're going to do is we're going to use format hex so we can look at the actual bits in the floating point numbers. Also, because doubles are represented in binary, it actually makes more sense to use values of h equal to 2 to the negative n, as opposed to values of h equaling 10 to the negative n. This will be more values of h, but it will also be more insightful. So we're going to run the following loop. Here, n goes from 1 to 53. H is assigned 2 to the negative n, and then we print out first the approximation that you learned in calculus, sine at 1 plus h minus sine at 1 all over h, and then we'll do it again with the second formula, sine at 1 plus h minus sine of 1 minus h all over 2h. All right, so let's start with this formula. So as h gets smaller by a factor of 2, it seems that we're getting 1 more bit of accuracy. However, at some point, it seems like the accuracy is dropping off. Basically, until we get an answer that is nonsensical. Well, the issue here is that the formula is indeed converging to the answer, but we found the approximation using a difference of 2 values that are very close to each other. Consequently, as h gets smaller and smaller, sine of 1 plus h and sine of 1 become closer to each other. Therefore, we have an issue. This is what we discussed before, subtractive cancellation. Let's repeat this, but now let's use this second formula. This second formula is actually going to get us a more accurate answer faster. In fact, as h is divided by 2, each time we get 2 additional bits of accuracy. But unfortunately, as h once again gets smaller and smaller, we lose the precision. And it's the same rate of loss. Why is this? Because once again, we are using an approximation that has to subtract two numbers that are very close to each other. Now, interestingly enough, this is a much better approximation of the derivative than the one on the previous slide, because it converges towards the answer faster. That is, at least until issues with numerical representations reduce the precision until we are left with garbage. So here are our two results. And you will notice that with this simpler formula, the best approximation came when h was equal to 2 to the negative 27, whereas with the new formula I introduced, the best approximation was when h was equal to 2 to the negative 17. So why does one formula work better than the other? When should we stop? How do we know when to stop in order to get the best approximation? Is there a formula that we can use to deduce that we should use 2 to the negative 27 in one case and 2 to the negative 17 in the other? Well, the sad answer is there is no such formula, because no matter what algorithm we create, mathematicians can come up with a function that is interestingly enough bizarre that our algorithm will be wrong. However, what we will do throughout this course is find algorithms that should be reasonable given some assumptions over what is occurring in the real world. And so fortunately, the real world is not as crazy as some mathematical formulas. Consequently, how are we going to find numerical algorithms that will help us get better approximations? Well, in this course, we are going to use these 7 tools in order to find numerical algorithms that will approximate solutions to analytic problems. These are weighted averages, iteration, linear algebra, interpolation, Taylor series bracketing, and the intermediate value theorem. All of these tools will be used either to find numerical algorithms or to analyze their error. In the next 7 topics, we will explore each of these, reviewing them, and look at how these can be used to solve at least simpler problems.